Welcome back. Okay, now we're going to get into a little bit of a scary territory that's a little bit more conceptual. We're going to talk about chaos in numerical models. And part of the problem is everybody uses the word chaos wrong. Like a kindergarten classroom is chaotic because there's so much craziness going on. That's not what we mean in a mathematical sense when we're talking about chaos. Your textbook actually just sort of glibly says something like a system of equations is chaotic when they are hypersensitive to numerical values used as input. I don't know that hypersensitive is even exactly a real word, but you get the idea here, where we're saying even little changes in the mathematical input to the equation, like the observations and so on, will make huge changes to the output of the model, which does not seem like a very attractive property of any kind of model. If you just, had like some small error in your observation that only changed its precision a little bit, or the accuracy a little bit, you wouldn't want that to like totally turn over your model to have your model give you a completely different answer. But sadly, that is how some sets of equations work. And we know that because of a meteorologist by the name of Ed Lorenz. Sometimes said Lorenz. Let's say Lorenz. Okay. Here he is. Good old Ed Lorenz. Old dead white guy of science. He was an American meteorologist who was working with numerical weather prediction models. And prior to that time, we had been aware that the equations that went into numerical prediction models were a mess. But it took Ed Lorenz to show us just how bad they were. Now, he was running a numerical weather prediction model, but let's be clear here. This was like in the 60s. This was not a very complicated model compared to modern mathematical models, the numerical weather prediction models that make the forecasts you see on TV, but it was the same source of equations behind it, running on a beast of a computer that looks like something like this thing right here, but the basics behind the idea were still the same, even though we're talking like 50 years ago. And so what Ed Lorenz did is he created a set of initial conditions for his model. He assimilated observations, like we talked about in the first part of this lecture, and created grids, analyses of the observations, and he stored them in files, okay? So like, this is actually random numbers here, but you get a sense of what they would have looked like, right? It's grids of, well, there was maybe a temperature at every grid point, and a pressure, and a wind speed, and a wind direction, and so on, associated with this early numerical weather prediction model. And so, like, I don't know, this is just sort of supposed to represent what one of his grids looked like. But what I want to draw your attention to is he had actually had the file saved out to 6 significant digits. So, like, if these are temperatures or something like that, I mean, he's measuring this thing out to, like, the millionth of a degree. Okay, obviously he had actually measured that height. That's just the output of his assimilation method, when it did the averaging and so on. It came out to all these digits. Then he fed it into his numerical weather prediction model, which God only knows what in like 1964 that was, in terms of how long it took it to run or something like that, but he got output. And, okay, this is not the output, this is just a modern weather model here, but like, we don't even need to get bogged down as to what this all is on here. This happens to be a map of the jet stream across North America and the Pacific Ocean, but it doesn't matter. Output, can you picture what I'm talking about here? He got output. Then the story gets a little bit less clear as to exactly what Ed Lorenz was doing, but for some reason he needed to run the numerical weather model again, for whatever purpose or whatever. And he needed to put his initial conditions, his analyses, back into the model as input again. And again, it's a little lost in the mists of history as to why, but for whatever reason he put in a different version of the input files that instead of having 6 digits after the decimal place, only had 3 digits after the decimal place, which is what I'm showing here on the right. Those are the same values as the table over there on the left. I just rounded them to 3 digits instead of 6. I mean, we're still talking about measuring temperature to the 1,000th of a degree. Clearly, these are equivalent well beyond our ability to measure, right? They were just the result of calculations that went through his assimilation method, and he got these calculations of, in this case, I don't know, they're fake, I made random numbers, but you could picture this maybe being temperatures or something like that. And he ran the model again, and he got output again. And again, let's just say this is a map of the jet stream or whatever. Again, I just pulled something off of a website today. But whatever. But here's what was totally shocking to Ed Lorenz. When he actually put the two model runs side by side, they looked, well, I was going to say totally different. They started off indistinguishable. The model forecast 6 hours after the start of the model run, like the forecast for 6 hours later, you couldn't tell the one that had started with 6 digits from the one that started with 3 digits. Maybe even 12 hours later, maybe even 24 hours later, they looked pretty much the same. But when he ran the model farther and farther forward, 2 days, 3 days, 4 days, farther and farther forecasts in the future, before long they looked literally nothing alike. The two model runs had diverged from each other. They no longer were telling the same story as to what the weather was really going to do. That is because Ed Lorenz had just stumbled upon the fact that the 7 primitive equations form a chaotic system of equations. Now, 50 years later, we actually know about lots of different types of systems of equations that are chaotic like this, where you have the system is very sensitive to the input, where even being off by a temperature difference of 1,000th of a degree gives you a different answer. Or we have mathematical models, for example, of the orbits of the planets, where if you are off by your initial position of, say, the Earth by as little as like 10 meters from where it is right now, do you think we know the position of the Earth to within 10 meters? No, of course not. You get a very different forecast of where the Earth will be in its orbit like 2 million years from now. They make no difference. The equations for like the orbits, you wouldn't think they'd be chaotic, but they are. Yes, at first it doesn't really matter. If you simulate the orbit of the Earth for the next few hundred years, you can't tell the difference between the orbit that you were 10 meters off from the one where you were exactly right. But over the course of like integrating that forward millions and millions of years into the future, the forecasts go completely wrong, and you have literally no idea where in the orbit of the Earth we are on a given day. There's a lot of these kinds of systems of chaotic equations. Possibly the one that's most fun is to think about the game Plinko. If you watch daytime television ever, you've seen on the TV show The Price is Right this game called Plinko. And if you've never seen it before, you've got to watch it. You're in for a treat. Basically, on this game show, the people get these kind of discs, and they stand at the top of this board that has all these little nails along the way, and they drop the disc, and it bounces, 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 bounces off of the nails on the way down. And at the bottom, there's sort of like little buckets that catch the little disc as it falls. And there's different prizes on each of those buckets. Now, if some lucky contestant on the show drops their little disc in, it goes bounce, 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 and lands on the biggest prize. I think in this video, this lady wins $10,000. Wow, how great for her. Then, what does she do with her next one? Her next chip, her next disc. They call them chips on the show. She puts it, of course, in exactly the same spot at the top of the board and watches it go down. And she never gets the same, so she thinks she's going to get exactly the same prize again, but she doesn't. Because the system is chaotic. Even tiny differences in exactly how she started the game. She'd have to have that Plinko chip in exactly the same spot on the board to the trillionth of an inch in order to make it follow the same path down. By even being a tiny bit off, by the time the chip gets to the bottom of the board, it's not following the same path at all. Plinko is an example of a chaotic system. Being a tiny bit off creates these kind of problems, where it doesn't go through. Now, Ed Lorenz coined a terrible term for this, and I guess as he went, I would not doubt he went to his grave saying I should have chosen a better word than this. He calls this phenomenon of chaos the butterfly effect, and you've probably heard some formulation of this about, like, when a butterfly flaps his wings in Brazil, it could lead to a tornado in Texas. I believe that's the actual verbiage from Ed Lorenz's paper in the early 70s. And that is an absolutely terribly misleading thing. Don't get the idea that the butterfly caused the tornado. It's more a matter of the atmosphere is now doing something different, than it's on a different path than it would have been if the butterfly hadn't done that. And that path might involve a tornado someday. I mean, not immediately, like somehow or other the butterfly flaps his wings and, oh my god, a tornado formed that wouldn't have formed. No, we're talking at some point in the distant future. At the present time and in the near-term future, it's all going to look exactly the same. Now, it's a bit of a theoretical, philosophical point as to whether it's the equations that are chaotic or whether it's the actual physical system itself. Is the atmosphere chaotic or is the math chaotic? But that's kind of a philosophical point that we're not going to go into. I'd rather talk about how we deal with it. I mean, now I'm switching. I originally had this broken up into two different PowerPoints, so the background has changed here, but Basically, everything that we have shown you so far about numerical weather prediction has been what we call deterministic modeling. Deterministic modeling says we take a model and we put in input into the model, and then we see what the output of the model will be. And the emphasis here is that it's a model. We have one model, one single model run, taking one set of input and creating one set of output is what we call deterministic modeling. But the truth of the matter is we know that there's lots of problems with that. We know that there are problems with the initial conditions. If we don't have those initial conditions right to, well, apparently more than 6 digits past the decimal place, we don't actually know if the model is forecasting the right thing, because it would be different if we had slightly different initial conditions. And frankly, there's also this issue of we have lots of different models to choose from. I mean, we've already seen in this lecture several different numerical weather prediction models like Eta4 and NAM and GFS and Alt-WRF, and the names aren't important. There's lots to choose from. So I know that if I ran a different model with that, or if I either ran a different model, or if I ran the same model with slightly different initial conditions, or actually it works out to slightly different boundary conditions, I'm going to get a different forecast. Well, that sounds like trouble. I want the forecast, not a variety of forecasts, depending on exactly which model I chose and exactly which initial conditions, how many decimal places I had, and so on. When I run a model, I need to understand, apparently, that to some extent, the answer I got was based as a function of the choices I made. And that's why deterministic modeling like that is actually way out of favor. A much better strategy is what we call ensemble modeling. Ensemble's a tricky word. Let me just put a definition up here. I like this second one here about it's a group of items viewed as a whole rather than individually. We're going to work with an ensemble of models. Not just one model, but lots of models. Actually, that first part is not a bad definition either, where it's like a group of musicians, actors, or dancers performing together. In this case, it's going to be a group of models performing together. But the basic idea is that in ensemble modeling, there are many, maybe very many, numerical models that are going to be producing forecasts for some point in the future. Each individual model that is part of this ensemble has a name. We call it a member. So we're going to run many members, each of which is a numerical weather prediction model of what we think the weather will be doing 24 hours from now, 48 hours from now, 96 hours from now, or whatever. And each member is going to produce, frankly, a different forecast than the other members in our ensemble. That might sound like a disaster, but that's actually a hugely beneficial strategy that helps us to understand not only what the most likely outcome is, but what the range of possible outcomes could be. Just to show you a dictionary definition here, this comes from the Glossary of Meteorology. It says ensemble forecasting tells us it is a set of different forecasts all valid at the same forecast time. Like they are all the forecasts predicting the weather on the 1st of December or whatever day or whatever. And the differences from the forecast are going to provide some kind of probability distribution. They're going to give us some sense of the range of possible outcomes. Let me show you this in the context of weather here. Weather forecasting is what is known in differential equations as an initial value problem. I originally had more slides about this, and then I decided you didn't need to know that much about what that actually means. I mean, we've already talked about initial conditions. I don't think you have trouble believing that the forecast depends on the initial conditions. So we're going to take those initial conditions. I mean, that's what we do in a numerical model, is we take the initial conditions, which have been made into analyses, and we apply the physics of the atmosphere to them. And the way that the atmosphere is going to change is going to be sensitively dependent, because it's a chaotic system, on exactly the values that we used for our initial conditions. But the truth of the matter is it's impossible to get perfect initial conditions. We don't even know what perfect initial conditions we would want, what those would even look like. But that's okay. We know the range. We know the initial conditions need to look pretty much like the real world. If you have enough computer power, let's try to get a handle on the range that we need. We can run a large number of numerical weather prediction models, an ensemble of these models, to get a sense of what's going to happen and what can go wrong in your forecast. Wait, does that mean we're going to be running not just... I thought, oh God forbid, I thought numerical weather prediction models were huge and created lots of output. Yeah. And now we're going to run a large ensemble of them, like lots of models? Yeah. This is going to be something you're going to run on a PC. This is going to be something that's going to be in some giant hall full of supercomputers all working together. Let me show you how we would do this as kind of an example here. Let's say we take in all the observations exactly as they are and just bring them in and compute initial conditions. Okay, so we go and we get all the observations, and we're going to call this run 1, okay, just to give it a name. So we took all available current temperatures and dew points and pressures and humidities and everything else, and we're going to make a set of analyses, and we're going to use that as input to our model. Now, one of the pieces of information that went into run 1 was the temperature in Omaha. And let's say the temperature in Omaha right now was reported as being 50 degrees. Does that mean it's 50 degrees in Omaha? No, of course not. That's just an estimate, okay? That is the estimate that came from the piece of equipment that did the measuring, the thermometer. The truth of the matter is, there's all kinds of possible sources of error, from rounding errors to systematic calibration errors to just the fact that, well, we only read it out to 2 decimal places, like to the nearest, tenth of a degree or something like that. In other words, we fed the model that is 50 degrees in Omaha. That went into the assimilation method that became part of the analysis, and now it's not the right temperature. Okay? It's not 50 degrees in Omaha. So run 1 is doomed to fail. There's just no way this is going to be right. We don't have the right initial conditions there in Omaha. Or maybe not. Maybe it turns out that the weather right now, because of the chaos of the weather, actually the temperature in Omaha is not that critical right now. Actually, over a range of possible temperatures in Omaha right now, we'd still get the same forecast of what the weather will be like next Saturday in Omaha. We don't actually know. So what we're going to do is we're going to make a second run of the model. They'll be like the second member of our ensemble, and we're going to just put in a fake value here. What if instead of saying it was 50 degrees in Omaha, what if we told the assimilation scheme that the temperature in Omaha was 49.6? Because here's the deal, we don't actually know. Okay? The real temperature is somewhere in that area, but these are all just estimates. If the real temperature of the air in Omaha was 49.6 or the real temperature in the air was 50, either way, you know what we would report? 50. That's what would come across from the observing stations. So we'll tell the model, okay, you know what? Hey, assimilation scheme, go make your initial analyses, but assume that Omaha's temperature is now something slightly different. We're going to adjust it slightly, just sort of within the range of what is a possible real temperature in Omaha right now, and we'll call that run 2. And we will have just randomly made some little changes to some of the observations that went into the model. Okay? The software just does this. It randomly says, okay, there's a typical range of errors for temperature or for pressure or for wind direction, and it just sort of randomly changes them and creates run 2. Run 2 has slightly, barely distinguishable differences between its initial conditions and run 1. But guess what? Because of chaos, when we run 2 out, it's not going to make the same forecast as run 1. I mean, they might start off being quite similar. They probably will start off the first 6 hours of the model time, the first 12 hours, the first 18 hours. But as time goes by, they're going to get different. Okay? Now, how far out and how different, that would matter. Maybe that's something we need to know. They might, though, get really different. Well, then what? Well, here's an idea. Let's just keep making more model runs. And in practice, ensemble modeling typically uses on the order of a few dozen numerical weather prediction models. Like in this example, let's just say 20. Okay? They will have run 20 slightly different versions. Well, it's the same numerical weather prediction model, but 20 slightly different sets of input. All of which are indistinguishable from what the real weather is doing. But each one is just a tiny bit different, and when we start simulating, they'll start off pretty much the same, but by, let's say, 48 hours out, we have 20 different forecasts. Well, that sounds like a nightmare, but that's kind of where the meteorologist comes in and says, different how? What changes? Why are all these models different? How many of them are similar? How many of them are outliers, and they did something that doesn't look very realistic? How big is the spread between the different models that went out? To visualize that, meteorologists have created a type of weather chart that has a hilarious name. They're called spaghetti charts. like as in the pasta dish. Let me show you what a spaghetti chart is going to look like. Now, this is not yet the spaghetti chart. We're going to build it. This is the output of some model. This is the output of a model. It happens to be making a chart about something meteorologists care about called 500 millibar height. It's how high above the ground you have to go to get to 500 millibars. And the archive I pulled this off of, this just happens to be the March 3rd, 2016 500 millibar chart. This could be the initial conditions. This could be the analyses that went into your model run. And instead of looking at this whole chart that has lots, areas of high 500 millibar height and low 500 millibar height, let's just graphically pull two of the contours off there. We'll just use two of those contours to kind of give us a sense of what the pattern looks like, where there's sort of a trough and there's sort of a ridge in the 500 millibar height here. Now, if I just put those two contour lines on the plot, that is what my model's depiction of the 500 millibar chart at least partially looks like here. And I'm now going to take my model and I'm going to run. This particular ensemble had 21 members. And if I take 21 members here and I make this, these are my, let's see here. This is actually the initial conditions then for 21 different model runs. And it's kind of hard to see that they're all basically the same. See how there's 21 different blue curves showing what the 21 different sets of initial conditions look like as far as where that one contour was. And there's 21 of those little red curves on there. Okay, showing where the second contour was. The yellow on there I think is supposed to be the average. And you can see that there are actually, if you squint, some small differences. I mean, the 21 model run started off with slightly different ideas about where the 500 millibar heights were higher and lower. But they're indistinguishable. Okay, I mean, we'd really have to squint to look and find the differences. Now, if we actually simulate this model forward 24 hours into the future, we'll get this chart. This is 24 hours simulated later. And again, we've just put 21 different models output on the same plot. And you can see by taking a look here, well, those 21 blue curves and those 21 red curves actually, they all look pretty much alike. I mean, the 21 blue curves are all pretty much on each other. Yes, some places the 500 millibar contour is a little farther south, some places a little bit farther north. There's a little bit of a spread kind of across northern Illinois and Indiana and so on, but by and large they're in pretty good agreement. In most places there is a relatively small difference. 24 hours later, I have pretty good confidence about what's going on inside of this red circle here, because all of my models, even though they had slightly different input, came up with basically the same output. There is good, here's a nice vocabulary word, consensus as to what the models are saying inside of that red circle there. Let's keep the model running. It's going to continue making forecasts, remember, every little time step, moving forward, 21 different models. Good Lord, this is going to take a whole building full of supercomputers to make this process work. 48 hours from now. Alright, so now this happens to be the March 5th, 2016 forecast. Well, the differences between the 21 members of this model are starting to get a little more apparent. I mean, if I actually take a look here, inside of this red circle here, well, the 21 red contours from 21 different models, all showing slightly different ideas of what the 500 millibar height looks like. Well, they're not all that different. But there are places where we're starting to get some weirdness. Like, for example, this feature in the red circle here off the east coast of the United States, that happens to be a little feature called a trough. But you can see how there's sort of a bend in those blue contours, and all 21 versions of the model have a slightly different idea as to where that trough is going to be. Some have it a little farther east, some have it a little farther west, some have it a little farther north, and that's going to make some uncertainty in our forecast right there. There is some disagreement within the model as to where the trough will be. So 48 hours later, we know that we are still pretty confident where these models have a lot of consensus inside of this red circle here. But, we're a lot less confident about what the weather is doing inside of this red circle off the east coast of the United States. But on the other hand, the ensemble of models is giving us a sense of the range of possible answers. I mean, they're all in agreement that there is a trough, that kind of dip there in the jet stream. They just have a slight disagreement as to exactly where it's happening. Okay? Gives us a sense of the range of possible outcomes. Let's play the same game with 72 hours out into the forecast. And as we take a look here, well, all 21 versions of the model are in agreement in a broad sense. Like inside of that red circle there, they're all in agreement that there's this feature called a ridge. It's kind of that upside down U-shaped thing in the blue contours there. They all are in agreement that there is some kind of ridge forming across the western and central United States. They have slight differences in terms of where, exactly how far east and how far west and how far north and how far south. But by and large, they all agree that a ridge is forming. 72 hours out, all 21 hours versions of our model agree. And all 21 models agree that there's going to be this big old trough in the northeastern United States. Broadly, then, I have really good confidence. That big old trough in the jet stream is going to happen with this, big old kind of U-shaped feature. The exact details of, is it here or is it 100 miles farther to the west or is it 100 miles farther to the south, I don't have that great of confidence on 72 hours out, but I'm getting a forecast. Frankly, this model run went really well. Even at 96 hours out, the 21 members don't actually have a huge difference in their forecast. You can see that the 21 blue contours are starting to get a little more spread out, and the 21 red contours are starting to get a little spread out. The 21 different versions of the model are starting to diverge. They're starting to show slightly different forecasts. But let's take it out to 120 hours. This is starting to look like a disaster. I mean, my spaghetti chart is starting to look a lot like spaghetti. If I take a closer look at the patterns that we see for the 21 different models, the 21 different models all have very different ideas as to where the pattern in the 500 millibar heights is going to be. They see different features. Although, frankly, by the standards of meteorology, these models are actually still doing pretty well, considering we're 120 hours forward in the forecast future here. But you can see now why we're starting to call these guys spaghetti plots. They're a big tangle of contour lines all going crazy, and they all are kind of on top of each other, and if they're all laying in the same direction, looking similar, we say that the model is in consensus. Whereas if they're crazy and crossing each other, the model is no longer, the ensemble is no longer in consensus. Moving farther even forward, here's the 6-day forecast, and you can see that the models are even less in agreement, or the 7-day forecast, or the 8-day forecast, or the 9-day forecast, or the 10-day forecast. I don't know how far I took this here. Let's just stick it with 10 days. Well, you can see by looking at that plot there, clearly all the different 21 different versions of the model that made up this ensemble now are telling us all wildly different things about where other troughs and ridges in the 500 millibar height pattern. We no longer really, at 10 days forward, have any meaningful information in this ensemble. We have no idea what the weather is going to do. But we got that information by interpreting these spaghetti charts. When the members of the model are producing forecasts that all seem to be in pretty good agreement, the meteorologists can have pretty good confidence about what the models are saying that's going to really happen. Turned out it doesn't really matter all that much what the initial conditions were. This is what's going to happen 24 hours from now, 48 hours from now, whatever. But when the model members are producing forecasts that are all wildly disagreeing and the contours are all over the place and crossing and so on, we have very low confidence in what the models are saying. We now know this part of the forecast is sensitively dependent on the input conditions. And we don't know the input conditions well enough to know which of the 21 models in that ensemble, which of the 21 members, to use the right word, is the correct forecast. One of them is probably closer to right. Now, in the case of ensemble modeling forecasts of weather, the main difference that we make from one ensemble member to another ensemble member is typically just the initial conditions. In practice, we also use ensemble modeling for other purposes like climate forecasts and so on, where the different ensemble members are actually usually the same input data, but we're running slightly different versions of the model. But that's more of a topic that we talk about in my ATS 105 Science of Climate Change course. Alright, this is a really long lecture. Let's answer a couple quick questions before we're finally done with it. Question 10. The main problem with relying on a deterministic modeling strategy is that the forecaster has no way to know in advance, A, if the weather's changing at all, B, whether or not the 7 primitive equations actually even apply in the current situation, C, he or she has enough computer power to run the set of models, or D, if the inputs to the model are accurate enough to produce an accurate forecast. Oh, what is the problem with deterministic modeling in contrast to ensemble modeling? Better make a choice from those 4 options and get a little feedback before you move on to question 11.